Okay, we want to look at constant growth rate models. Now, growth rate we're going to symbolize by R, and you can think R equals 0.05 if you've got 5% interest. So your money is growing at 5%. Now, growth rate is not rate of change. So we might maybe want to make an important note here. Rate of change means something completely different. And we should be pretty familiar with what rate of change means. Okay, so a growth rate, if the growth rate is R, then every period or quantity increases by R times the previous quantity. So again, in the interest situation, if I've got $10,000, my growth rate is 0.05, then in a year, my principal will increase by 5% of $10,000, or 0.05 times $10,000, which is $500. And then we have $10,500 in the next year. It'll grow by 5% of that. Now, rather than multiplying by 5% and adding, as I just did, we have this thing called the growth factor. Now, I haven't really talked in the course very extensively about growth rate and growth factor, although your textbook does, but they're natural concepts that you might find helpful. And you've seen them, so just putting words on them should be helpful. Growth factor is 1 plus growth rate. So your growth factor would be 1 plus 0.05 or 1.05. So there's your growth factor. Now you know if you have a principal function, and we're familiar with the idea that you raise your 1 plus 0.05 to the t for t periods, meant for t years in this case, and you get your principal function. And this is nothing but your initial quantity, which is, in this case, P naught, times the growth factor raised to the t power. This is an exponential function. In the general form of an exponential function is like y equals a b to the t. So b is identified with your growth factor, which is just 1 plus your growth rate. So in this case, we have our 1.05 to the t, we have our initial quantity, which is like the a, in our p of t, well, that corresponds to the y. So this is an exponential function. We can determine its doubling time. We can do just about anything we need to. Now, if this is a population of an animal herd or something, well, maybe that population is growing at 5% per year. And right here we have another model. Okay? If it's radioactive decay, your growth rate is negative. and that would be like negative 0.05 if the activity decreases. I'm going to write 5% correctly yet. Okay, there we go. Decreases by 5% every period. Now, when we're doing compound interest, the natural period is a year. And we're doing just basic yearly interest. The natural period is a year. If we're doing compound interest, where we compound a number of times during the year, then our growth factor would be 1 plus 5% over whatever number of times we're compounding. And then our exponent would be the number of times we're compounding times the number of years, because the period would just be one compounding. So we'd have a certain number of compoundings in a year. Then we've been over that, so I'm just kind of relating this to what you already know or should know. Okay, so radioactivity. So we decrease by 5% every period. Now with radioactivity, sometimes things take a long time to decay. Certain isotopes of uranium can take 1 billion years to decay down to half. So their annual growth rate would be very tiny. But their growth rate over, say, millions of years, a period of 1 million years, might be something you could actually focus your attention on, or even over 1 billion years. But some things decay very quickly in just a few seconds. So the period would depend on what the substance actually does, but the model is going to be what it is. Here's your growth rate. It decreases by 5%, so your growth rate is negative 0.05, so the growth factor is 1 plus R, which is 1 plus negative 0.05, which is 0.95. So the model is like y equals a b to the t, where t is the number of periods, whatever period it takes to decrease by 5%, b equal to 0.95, a equal to the t equals to the amount when t is 0. Okay, so we could say, okay, if you want to talk about radioactivity, we could call it R equals R naught times 0.95 to the t. That would be our model. Now, if we don't know what the original amount is, for example, but we know if we don't know the original amount, but we know what the radioactivity is at some time, like 10 periods, then we can plug that information in here and solve for R naught, can't we? Or if we have a radioactive decay situation where we've got radioactivity at one point, at one time, and then at another time, we'd have 2 data points. We plug those 2 data points in, we do a model of this nature, and of course we know how to do that. So this is kind of the way constant growth rate models work. I didn't address compound interest, but that's something we've done quite a bit of, so yeah, you should review that, obviously.